I'll just give a very brief introduction and
Yeah.
Vinod will take over. Vinod has done his MTech and a PhD from IIT Kanpur. He worked under Professor Vinay Namodari. He was also who was also my guide, and he was awarded outstanding thesis award for his PhD thesis on domain adaptation. Right now, he is doing his postdoc in Belgium, KU11, and this is his GitHub page where there are more details about his recent work. Yeah, Vinod, you can take over.
Yeah.
Thank you.
Yeah. Thanks, Ravi. So today we will discuss about the domain adaptation, particularly related to the computer vision problem. So there are a lot of methods are there, but I will mostly talk about the method. Those are based on the adversarial setup. So we will see what the adversarial setup and how the domain adaptation is applicable for that particular setting. Before going to start, I will the brief introduction about the deep learning. Like deep learning or machine learning are very popular in many computer vision related problems, such as classification, or it could be a localization, detection, segmentation, generation, all these things. So these are basic what is the advantage or applications of the machine learning or deep learning based methods. But what problem occurs in these machine learning setup? First, we require a lot of training data for that particular problem, and second thing is that this is the most important thing actually. They are biased toward one particular data distribution. For example, what's the mean of the data distribution? For example, if I have images of this neat and clean background, like the monitor images, and I train model with such kind of image. If I test on the similar kind of images, then performance goes some 98% or more than it. But what happens when I train the model or the algorithms or on these neat and clean images or one kind of images, but test on the different kind of images, the performance goes very like drastically decreases. It goes from like 98 to 59%. So the reason is that like these two images, or what I mean, these two kind of images are come from the different distribution. What the mean of the distribution means? They have one particular kind of setup, uh, and other data set has a different kind of setup. They have some different lighting condition, they have different what mean the pose or different environment. All these things they have different that sense. So we will call it a distributions. So actually in this problem, we don't need to access or what means estimate the full distribution. We can only work with the samples. Like suppose we don't need to estimate what kind of distribution uh, uh, these images come from, and we just need to the samples. So we will see what the domain adaptation. Domain adaptation is a method to like, or it's a transfer learning method where we the objective is to adapt our model for other kind of images. For example, we have given the labeled images for this data set, but we want our model to work on this another kind of setup or another kind of images. So in that kind of application or kind of approach, we need a domain adaptation. So in domain adaptation setting, what we have provided, we have provided a label data set. I will call it a source data set. In this example, if I provided the labels for this left side of images, I will call it a source data set. And we also provided another data set, which is target data set, and this unlabeled. So these images also provided, but we don't have the label for these images. Label, it means what the class. For example, we are solving the classification problem. So what the class of these images. So this is the general setups in the domain adaptation. As I said, due to the various distributional difference, these two data sets are different. They have some discrepancy. Because of it, the model is not perform well when we train one kind of data set but test on the different data set. So how to do that thing so that our model can work for both the data set, or particularly in the target data set, because we are mostly interested in the target images where we don't have the labels. So Before going to start, like I just basic motivation how to do it. So in general machine learning setting, what we have given the training set. Training set means we have the labels and the images, and we have come up with some model. So we will call it training phase. So here we train our model with these training images, and similarly this model is used for the test setting. So we have the similar kind of images we generally use for the test split. Like in general, like in machine learning, we will divide the data set in train, test, and val split. So these split are from the same kind of distribution. So this is a typical machine learning setup. So it's we call evolution. And this I mean from the like training model to the actually evaluation model, we will just call it deployment. So we have to deploy for particular task. So in this slide we evaluate the performance, and we are okay with performance, because I mean the performance will very nice, because both training and tests come from the same distribution. Main problem occurs when we change the test distribution, or what the test data set. Suppose this is the MNIST data set, and this is the MNIST M data set. So MNIST data set, we train our model on the MNIST data set, but test on the MNIST M data set, the performance is not satisfactory. Reason I told you, because they are from the different distribution, and model only cannot adapt for the new setting of the data set. So model only learn model only learn from or the parameter. So how to suppose this is our end task, and we want our model to work on this particular task. What to do in that case? First, I mean the basic naive-based approach. What we can say, we can use the same training set as we want a test. So here the training set is same and test set both are same. I mean same means both are come from the same distribution. Then the performance will good. But reason is that we need a training set. We need a training set, we need a labels, and it associated with the label. Suppose we have only label data for this MNIST M, and we want it to adapt for the MNIST M data set. What to do in that case? So this is the domain adaptation method. Here okay, so here the performance is very nice, because we can say that these two images, training and test, are from similar. So like the equal to, it means like both are from the same distribution, and the performance is not good because for the MNIST, we train on the MNIST and test on the MNIST M. The performance is not good because both are not from the same distribution. So that's the basic what means problems, or what we can say requirement of the domain adaptation. So here what we can see, like why if we train our model on this kind of images and test on this kind of image, model will perform very well. Why I can say this? Because both are images very similar. I mean train and test, or working at source and target, both are similar. Here are the this gives some kind of intuition or motivation what we should need to do. So for example, if I train our model on this kind of images and test on these images, what's the performance? We can see the performance will not go, because both are visually different. I mean both background, what we can say, both distribution are different. So the model will not perform well on these images if we train on these images. I mean if we train on the left side of images and test on the right side on image, the model will perform very well, because both are look similar. It means both are from the same the data distribution. So how to do this thing? So one observation, or what means one motivation we can see, that somehow we will make these source and target distribution target images similar to each other. I mean, so we will not work on the images, we will work on the feature space. Suppose somehow we will generate features or obtain the features such that source and target feature look similar, then we can solve the domain adaptation problem. That's the motivation. Here the bottom row will very good for the learning, because both are from the same I mean both images are look same. If I will talk about the features of this left side and right side images, or the bottom line will be same, I mean similar. So that's why the model will perform very well. Here in the top row, the features of this image, this kind of images and this kind of image are different. so the model will not perform. But somehow if we make the feature similar, then we can adapt our model for the new this domain, like right side domain. So this is like basic intuition. We have to make minimize the discrepancy between these two domains in the feature space. So there are some methods like how to minimize. So one method could be like we can measure the mean maximum mean discrepancy between these two domains, and we can also align the correlation between correlation features of these two data set, source and target. We can also use some other method like GANs, like image generations and feature invariance kind of setup. But actually what happens when we happens like what we want a features or what a feature that are domain invariant, like they don't have the domain information but they should have the class information. So we want a feature which has a domain invariant but class variant features. So when we are trying to make the features invariant to the domain, we may lose the class information property, and that's why they have like they can multiple classes can merge together. So in some of their issues come when we are solving the domain adaptation problem. So we will talk about some of these issues in this upcoming slides. So okay, so come to the adversarial setup. So here we have some defined loss functions, like how to minimize the discrepancy between the source and target. We could use some kind of for example, we can use the equilibrium distance measure, or some other new what we can say the discrepancy measures that can solve the problem. But adversarial, so we have to design what kind of loss function we are using. But adversarial learning has the benefit that it has like it's learnable loss. We are not defining the what kind of loss, what kind of space they are map, and they are minimizing their discrepancy. It will learn automatically by itself from the data. That's why we are focusing on the adversarial learning setup. So here I will talk about the adversarial setup in this next slide. So suppose in this figure, we can assume the red points are the source domain and the blue points are the target domain. And we have provided the labels for the red point, but we don't have the labels for the blue point. Sorry, we have the labels for the red point, but we don't have the label for the blue point. And the object star, whatever is the source or target, whatever. So sorry. So here, if we have the source data point, label data point, we can learn a classifier which actually classify the red point, like between the circle and the star. There's no issue in that point. But we can observe that this classifier is not well suited for the blue point. I mean, it's not classifying red, star versus circle of the blue points. So that's the basic problem. Here we need to adaptation. So why this happens? Because there exists a discriminator, there exists a classifier, I will call it domain classifier, which can classify the red versus blue point. So they have a discrepancy. Somehow we transform these features in some other space where we cannot find any discriminator which can discriminate between the red versus the blue point. Then the classifier train on the blue red point will also equally work for the blue point. So this is the basic. So I will repeat the same thing because the important concept in the adversarial learning here. Suppose like here these discrepancy occurs because the blue point and the red point have there exists a classifier, or we call it a discriminator, which can discriminate between the red versus blue point. If somehow we will make this feature in such some space where we cannot discriminate between the blue versus red point, then if we train the classifier on based on the red point, the same classifier will also work for the blue point. Here we can see the examples here. After the adaptation, the same classifier, the classifier is actually trained using the red points. And if it's classifying the red circle versus red star, then it's also equally blue star versus blue circle. So that's the basic adaptation process. Here actually we cannot find any domain classifier which can classify the red versus blue point. So somehow we have to make here the features are domain invariant because it don't have the domain discrepancy or domain domain knowledge in these features, but they have the class discriminator property. That's the whole objective of the adversarial learning in the domain adaptation. We want a we want a feature that has the domain invariant and the class variant feature, which we have to learn. So in general, like mathematical, what we see in general problem formation, as I told, like we have provided a source data set, which is the label data set. So I will denote the S or DS. DS is a subset, or is come from the distribution S, and some NS examples for the source data set. Similarly, we also provide the target data set, and target data sets come from the distribution DT. T and DT is the samples. So here we don't have the labels for the target set, and the assumption is that both domains share the same label space. What the meaning of the label space? I mean, number of classes and the exact number of classes are same for both source and target. For example, here we have the 10 classes for MNIST data set and 0 to 9 digit. Similarly, target data should have this same classes 0 to 9. So that's the basic assumptions about the domain adaptation problem setting. So this is a popular data set. I'm not going to discuss about the data set, because each data set have the, like here for example, Office 31 have 31 classes, and each domains have some different discrepancy, or different what means the capturing condition, or the inherent noise, and all these things they have. So they are from different distribution. Similarly, we have the Office home data set, image lab data set. These are the standard data set in the domain adaptation setting. Okay, so this is some examples like of these three data sets I will talk about. So okay, let's come about the some related work in this field. Here method I told, like we have to minimize the discrepancy between the source and target features. So for example, we obtain the source feature here in the similarly we can also find the target features, and we measure the discrepancy in terms of alignment between these two features, and we will try to minimize this thing. If we try to minimize this thing, it means like we are making the source and target feature similar to each other. In that case, if the classifier train on the source feature, it will also work for the target feature. That's the basic objective. So these are some discrepancy with methods. People have like tried to what can say, propose some new discrepancy. It could be like conditional Dan, or Jada, or Coral, MMD, whatever. So this is basic discrepancy with method. Come to the adversarial learning setup, which is like in this talk we are talking about mostly. So here the basic paper comes in the like 2015 something. So here they use actually a discriminator setup here. So this is the feature extractor, green part, and blue part is the traditional classifier, and red part is the domain classifier, or I could call it the discriminator. So what happens, like when we pass an images, or what we source images here, source images go to the classifier, and the classifier bits will be updated on the source classification loss. So in the classification loss will update the parameter of the classifier as well as the feature extractor. So this is basic feature extractor obtain the features, and the source and target feature both are passed to the discriminator, and discriminator will try to discriminate between these two things, like source versus target. But we want the feature which has a domain invariant. So we will make what we say, we will use the negative sign of the gradient to update the parameter of the feature extractor. So what's happening here, the features extractor will try to make a what we domain invariant feature. Domain classifier will try to separate them out, and based on the feedback, or what is the gradient base, the feature extractor will learn like what is the like the domain information domain classifier using, and it will try to suppress them. So that's why we will obtain the domain invariant features here, but because of the classifier we can actually obtain the class variant feature. Just that like two-way watching the class, or the min-max kind of game. Here the feature to minimize the classification loss and maximize the domain. But the classification classified network is tend to minimize the classification loss, and the domain classifier tend to minimize the domain loss. So domain classifier and the feature extractor will play a, like say min-max kind of game. Try to minimize the loss. It will try to maximize the loss. So this is basic typical setup. But what's problem here? The discriminator is not using any kind of class information, so it can change all the features in one class. So it might lose the class information property. It can give the domain invariant features surely, but it can lose the class information property. So next work for each class they use the separate discriminator. That's why they will hold, or what is the capture, or they will not lose the class information property. That's the MADA paper. But what we can see here, the basic issue is that, like, when number of classes increases, the number of discriminator will also increase. For example, suppose I have 1,100 of the discriminator. That's too large, I mean too huge to train the model and to optimize the model. So this is not feasible for the practical learning setup. So we can come up with a new discriminator setup which actually can hold the class information as well as the domain invariant setup with a reasonable amount of resources. So as I told that they have the adversarial domain adaptation method suffer from the mode collapse. Mode collapse means like when the two classes or multiple classes are merged together, like for example the car and tracks are come in the one category, so they have lose the class information property. And so similarly, misalignment means when the car goes to the track side and track goes to the car side. So that's the misalignment setup. And also some of the methods are depend upon the source classifier. I mean, so here in this MADA, they actually use the source classifier prediction to choose which discriminator we have to use for one particular class. So there's a dependency on the source classifier, and the models are complex, as I told, like they have the when the classes are increases. Someone has posted some question. In the DNN, shouldn't the classifier help in the preserving the class specific feature while they are being yes, so classifier definitely will try to preserve the class information, but actually it's work on the source side only because it's using the source data set. So but we are talking about the target. So it might sometime happens that the source data has larger size, so it will what will deviate in the source side, but it will not work for the target. Sometime happens. I will show some examples here in this example why when this happens. Okay, so sorry. Now come to the so what we can use the source level structure in the discriminator. That's the basic intuition. So here in this method, what we have done, instead of the binary classifier, we use a multi-class discriminator. So why we use multi-class discriminator? So it is a similar way as we can use the each discriminator for each classes. It can solve that issue. I mean, it can work similar to that setup, but it is not like it's not exponentially increase when number of classes are increased. For example, if we have the 30 classes, then we can use the 31 plus discriminator, 31 class discriminator. So the discriminator objective is to not to divide them in the source versus target, but it's also divide like it's like target versus source classes. So suppose it has a n classes, so we have n plus one discriminator here. Because we don't know the target classes, we cannot divide the data. What means we cannot classify the
Is the speaker
classes.
audible?
Yeah. Sorry.
Yeah, I could not hear you for a brief time. I'm not sure.
Yeah, like last,
Oh,
after you started this slide, for a while, your audio got cut.
Oh, so I think from where I've discussed in the informative discriminator in the slides.
no, just that
No, that's just the
slide
same
where
slide.
you were talking about n+1.
Here,
Okay, okay, yeah. Sorry. So here the objective here to learn the I mean, so here we use the n+1 discriminator. So for the source data, for the target data, what happens? Like when one image comes here, so here we are using its adversarial setup. So the correct class will misclassify with any one of the classes. Since, for example, the correct class, target class is the car, so it will classify with any one of the classes of these things. So it will not merge with all the classes. In the instead of the binary discriminator, it will merge all the classes, all the source classes to the target classes, and all the target classes to the source classes. It will like confuse that thing. Here only samples of the source class, so target class will merge any one of the source classes, so it has some kind of class information property. But for the source samples, discriminator classify all the source samples to a single class. I mean, it could be a target class. So in that case, like we are actually misaligning the class information property for the source data. So but fortunately we have the labels for the source classes. So classifier loss, or what means the classifier will handle this thing. So for the source classes, it will not try to lose the it will not try to give up the class information property for the source. And target will since we are misclassifying with target samples any one of the source classes, then it's also have some kind of one the source, so target class will classify to the one of the source class. I mean, so there is no mode collapse. Mode collapse means not two classes of the target are merged together. I mean, each target class will only misclassify one of the source classes. So that's why we are avoiding the misclassification, or what we say, sorry, mode collapse problem in the domain adaptation setting. So this is basic informative discriminator. We can also expand this thing to in some selective samples based informative discriminator. So we can only use the samples which are more confident in terms of like they have the good prediction. Then we can only do those samples to train the multi-class discriminator. So this will also give some better performance. So this is some what we say incremental work of the EDA. So this is basic loss function.
Sorry
Yes.
to interrupt, but can you repeat that reason for mode collapse again? The reason I interrupted you was because if I don't understand that, probably I might not understand something either.
Okay, so mode collapse means like in the binary discriminator, what happens like when a one class of the one images of the source data will misclassify with the one class of, I mean all the classes of the target. Because here like here for example, all the source classes will misclassify with all the target classes, and all these target classes will misclassify by the I mean to the source classes. So they have kind of clusters, all the source, all the target. So they don't have kind of class information things in the discriminator. Here in this case, in the when we use the multi-class discriminator, the what we say the target class, or what we target image will only misclassify with any one of the source images. Because so since we are using a negative gradient, or what we say adversarial setup, so it will try to maximize the loss with by using only assign to its class to any one of the classes. It will not try to assign this particular class in all these remaining n classes. It will try to assign the class only one of the classes. So it has like all the samples, or what we can say the target samples will only go into one of these which confused with but only one of the source classes. That's why it's try to avoid the mode collapse. I hope did you get the answer, or should I explain in another way?
Vinod, maybe I'll refresh that. Tell us if I'm right, because if I understood it right. See, in the earlier case, all because the target domain doesn't have any labels, all the target domain features can be kind of made similar to look like one example of the source class, right?
Yes.
Hence the mode collapse is happening. But here, at max, one target domain example can be confused just with one of the source class labels. So only one class label is wrong here.
Yes, exactly.
So we are like, by that just using that, we are essentially making, instead of collapsing everything into one, we are at max doing one wrong.
One wrong, yes, exactly.
Okay.
So
Actually, the reason I had asked that question was because I started wondering why we have a classifier part at all then. Because here you anyways learn that the features are supposed to be for which class of the source.
Okay, so if you observe this carefully, actually what we are doing is wrong in the sense like here for the source samples we are asking the model to classify them in correct class. Here we are for the source samples we are saying discriminator to misclassify these samples. So here the weighted for the, I mean here the lambda what means some lambda parameters are there. So this control this thing. So the effect of the for the source samples will not go here much. I mean, the features will not be more updated, which the discriminator is morely updated because the classifier. So so that's the like here we are doing reverse thing. You can see like here the objective here to classify this thing, here you have to misclassify this thing for the source sample. Target is clear. Target, there is no confusion because we target samples only using the discriminator setup. For source, here we have the different what means the contradicting things, but because of the what tuning parameters, we can optimize these two losses, what mean two criteria, two problems simultaneously. Like, so we will give less weight to this part and more weight to this part. So actually classifier is handling this for the source samples, and the multi-class discriminator is mainly for the target sample. That's the in general. So classifier is very important. I mean, because of this, we cannot obtain the class informative properties. I mean, the correct class informative property.
Good. Thank you.
And how the background is handled here?
No,
Vinod?
so I'm not the example of background is just kind of sake of visually understand. So there is no background and foreground thing. So in the next work, I will share. I mean, I will tell what the background, how the domains are moving. I mean, how the adaptation process is going on. So so the background thing is just for the example, visually how they two domains are different to each other. Okay, so these are some performance. So I'm not going to discuss because this numbers are there. That's not important. Like, yeah, obviously, like so some methods are good. So the EDIS is much better than EDI, and EDI is more better than GRL. So this is when we are using the binary classifier, we are using the 80%, but when with the EDI is 88.7. So this is huge performance because of the mode collapse things. I mean, we are avoiding the mode collapse here. These are results on the all the data set, and there are some discrepancy was kind of measure, like we can measure the discrepancy between the source and target. It's less, it's better. I mean, we have the less discrepancy between source and target features. So we can, I mean, we can see EDA is giving better as compared to the binary discriminator or multi discriminator setup. So this is some basic visualization of the PSV. So here we can see in this GRL, GRL means the binary discriminator problem, binary discriminator setup. Here we can see they have the the features are bell what we can say domain invariant, but actually they have lose some of the class information, what we can say class information property, or what we class variance things. But in the EDA we actually have the more clean cluster as compared to the GRL. So that's way we can see that in our this EDA method is actually capturing the class information as well as the domain invariant features. So this is some other performance issues. So I'm not going to discuss because I have to cover one more work here. So in the like we come to the probabilistic discriminator. So in the previous work, what we have seen that we have to adapt the full features or full images. We are not focusing about like someone is asking like how the background and the foreground adaptation helping. So next question is can we do some more intelligent way to like adapt only which part which actually need to be adapted? I mean, why we need to adapt full part? Suppose we try to adapt one part which is not which has some noise or which has some problem, and it will give the negative impact on the models. So we have to obtain which part have to adapt. So here we use some kind of probabilistic discriminator. Based on the probabilistic discriminator means like the discriminator will also tell about the uncertainty estimation, how much it's uncertain about one particular prediction. So in this method, we actually use the two types of uncertainty. One is the data uncertainty, second the model uncertainty, epistemic aleatoric. So model uncertainty means like how much the model is uncertain about its prediction. I mean, because of the model's capability, it's not able to predict, and it sets some confusion. So the model uncertainty. But data uncertainty is something different. Suppose data has some inherent noise or some kind of inherent some kind of confusion. Okay, so as I said in the previous work, we are trying to adapt the full feature vector, or what means the full features or full images in the target of the target domain for the source classifier. Here we can be obtained some kind of intelligent way to obtain only the features or the part or the pixels or the regions which are actually need to be adapted. So here we use the uncertainty measure to obtain which region should be adapted. I mean, which region should be ignored and all these things. So we use the uncertainty estimation of for the discriminator only. So here we use the two uncertainty, model uncertainty and data uncertainty. Just think about it like a data uncertainty is the data has some problem. data has some occlusions, data has some kind of inherent noise, then the prediction is not correct. For example, the dogs and cat are look similar, so I mean they are so we cannot decide it's a dog category, the cat category. Similar in the model uncertainties, the model is unable to identify the dog versus cat due to the sufficient data. So that's way they have the model uncertainty and the data uncertainty. So this is some basic visualization of the how the uncertainty looks like. So currently this is not making any sense. I will explain, then this figure will make sense. So I will use generally I will use the certainty part. So it's the opposite of the uncertainty. Certainty means this the data has what means the image has more certainty, or what we say in this part to predict as it is a bag. And we can and similarly the the predictive uncertainty. Predictive uncertainty is the combination of the aleatoric and the epistemic. I mean, model uncertainty and the data uncertainty. So we can observe that the predictive certainty and the classifier certainty are both aligned to each other. I mean, if the model is more certain in this particular region, actual classifier using the same region to predict it. So that's the basic motivation about the the how to how to use the uncertainty in the domain adaptation setting. So here this is a basic example. I'm walking see the proposed model. Instead of the binary discriminator, as in the previous work we have shown binary discriminator or multi-class discriminator, here we use the Bayesian discriminator. So Bayesian discriminator is also gives the prediction of the about the domain class. It can also predict the how much is confident about its prediction. I mean, it gives the aleatoric uncertainty or data uncertainty. So why this happens? So discriminator, suppose discriminator is giving the more uncertainty prediction. I mean, it's more uncertain about its prediction about the domains. What it means? It means it's uncertain either the features or the images have already adapted. I mean, the adaptation is completed, then it's confused. I mean, it's not sure this is a source domain and target domain, then it's more uncertain. That's one reason. Could be if the uncertainty very high. A second reason could be it has some kind of data has some kind of inherent noise. I mean, if we talk about the data uncertainty, suppose data has some kind of occlusions, lot of noise are there, then that part, because of that part, the discriminator is uncertain about source versus target classes. So in both the cases, we have to avoid that region. So how to obtain the region? We just use the backward propagation to obtain the gradient, which gradient actually activated. I mean, we have the some kind of feature map, and which part of the feature map actually activated for giving this prediction, giving this uncertainty. So these regions actually these regions are actually associate or what reason for predicting the uncertainty. So suppose discriminator is uncertain, so in that part we have to avoid that part, and we will not we should not use that part for the classifier, because if the part is already adapted, then we don't need that part to be update further. If that part has some inherent noise, then also we have to avoid that part, because it is not capturing the kind of more information in the image, or it can deteriorate the performance. So we have to avoid where the discriminator is uncertain, and we have to attend where the discriminator is certain. I mean, so we can use the certainty as a reverse of the uncertainty. So we will attend the part where the discriminator is more certain. Discriminator is more certain, it means discriminator is more sure, as this is the source and target. And so we can ask the discriminator, okay, you are certain about the source versus target classification, which part you are from which part you are taking this information. So using the gradient, we obtain the which part, and we are giving more important to that part for updating the feature extractor as well as the classifier. This is the basic intuition about the part-based learning, what means adaptation. So first, suppose the image giving in this, so I will explain this in this slide. Suppose in the epoch number 5, suppose the discriminator is giving this part, epoch number 21, this part is more what we can say, this is a more part which is certain about this prediction. So okay, feature extractor will update this part, and now again ask the discriminator which part because of which part you are able to identify the source versus target. Then discriminator will tell this, because of this part I can identify the source versus target. Okay, then feature extractor will update this part, and it means hide this part, or what means make it the domain invariant for this part only. and that's with the progress going on. At the end, what happens, this attention part, what we see, the discriminator's certainty will not change. So then we can say model is converged, and then again we don't need to adapt. So in this way we are going actually part by part. This part is adapted, then we go to the next part, and the next part is actually we can adapt that part or not. If not, then we can ignore that part. If we can adapt, we will adapt that part. That's why we are going in what means some random, not random, based on the certainty or uncertainty prediction of the discriminator. So there's a basic intuition about the what we say this work. So there are a lot of equations, or I mean a lot of equation, I mean we have to obtain the uncertainty and all these things. So I'm not going to discuss about, because there's a separate work where people used to use how to obtain the better uncertainty. So we use the basically the alloteric and epistemic uncertainty in this work. So this are in Gall's work. So where we have to obtain, we have modified this uncertainty estimation for the domain adaptation by using some kind of, we use the p value. So we only use the positive activations rather than the negative activations here. So this is some minor details here. So maybe you can go through the paper if required, or maybe you can contact me if you need some more clarification on this thing. So so here we have some loss function. The loss function is like for the classification loss function as well as discriminator loss function. So for the classifier and the feature actor, we have to minimize this thing, and for the discriminator, we have to maximize this loss function. The basic typically adversarial learning setups here. So here we can also visualize the uncertainty, or what we say certainty is aligned with the classifier prediction. So we can also see that the where the discriminator is certain, it means the classifier is also looking the same regions for predicting that class. So this is not only for the source, which also target is also aligned with value where the target data. So the first row is the target, the second row is the source. So sorry, the first part of this is source, this second is the target. So in the also improve the performance with large margin to GR finite discriminator instead of use the Bayesian discriminator when it's go to 74 to 80 in this particular setting and AlexNet. So here, for example, in the DAN we go some 80%. Here we have the 89.5 to 10% improvement approximate. So this is some same feature visualization as I told in the previous work, where we should have the class information property as well as domain invariant property. So in the DAN we don't have proper what means the things, but here property like CADA is the identity the so in this like mostly view the how we will actually visualize the how the you can say the adaptation is going on this epoch wise. So methods so we can actually visualize the adaptation part. Okay, so that's third. So now I will quickly finish the last part of the slide. So interesting work, like so I can see like this is a source free domain adaptation. So in the previous work, all these work what we have seen that we need to adapt for the target data. I mean, so here in this work we don't need a source data at a training time. So that's a basic advantage of this work. So this is a source data free domain adaptation. So now what happens when we have to minimize the discrepancy between the source and target, we need kind of source data and target data discrepancy. But suppose we don't have the source data, what to do? We only provided the target data. If we only provided the target data, then actually we need something about the source data information, how to obtain. So suppose some people someone has provided a classifier, and the classifier is trained only on the source data set is given. So here we have provided two things. One thing is the target data, which is unlabeled. Second is the classifier, and the classifier is trained on the source data set. So we cannot access the source data and its label. We only can access the classifier, one classifier which is trained only on the source data. So in this work, actually we use the generative models to what we generate some samples, or what we can say some proxy samples for the source data, then the adaptation part. So here I can go directly into this what means figure. So suppose this pre-trained classifier is trained only on the source data, we can only access this source data. So here we use the conditional generator or what is GANs, conditional GAN. So the conditional GAN will take some random noise vector as well as some class conditions. Based on the class conditions, we will generate one particular class, and we will check if this generated image are the same class or not. For example, here we are generating the 5-digit class, and the generated some 6-digit class. It will classify, will provide some loss. Based on this loss, we will update the generator to enforce the generator to generate only the 5 class digit, whatever we are providing here. So this is basic typical. So here in the generator we also have the GAN discriminator. uh, since here we are not using any source distribution information here, so we are assuming that the pretrained classifier is trained on the source data. uh, so source data, so we actually capture the source data distribution. So how to provide these source data information to the generator? So we use some kind of energy function modeling. So we model this pretrained classifier as an energy based function. So this is typically what means the equation. So we use the likelihood, and based on the likelihood we use we convert it the energy function, and based on the energy function, actually, and what the energy function is just gives about the distributional information to the generator. Sorry. So sorry. Yeah. I just sorry. Yeah. So it's give the so here the generator will train only on 3 losses. One loss from the cross entropy loss, which is like misclassification generation. What classes it generated, and this misclassify about from the pretrained classifier. Second, in the this is energy function, I will call the log sum x. So this is a well-defined loss. And other thing is the GAN generator loss, GAN discriminators loss. So for training the GAN discriminator, we need actually some real data. So since we don't have the source data, but we can have the target data. Since GANs we don't need the label for it, we can use any unlabeled data, and target data is completely unlabeled. So we can use the unlabeled data to train the generator, or what is the GANs. So in this case, what happens, this unlabeled target data will help GAN to generate some natural look images, and this pretrained classifier in the cross entropy loss and the energy function loss will try to learn the source data distribution from the generator. So the from this setup we can obtain the generated image data. Since we have the conditional gains, we can give some condition and what class condition, and we can generate that digit. Using that labeled generated data and unlabeled target data, we can have a typical or what is the previous domain adaptation method, where we have a feature extractor, classifier, domain discriminator, and we have some gradient reversal, all these things to adapt this model for the this target unlabeled target data. So this is a basic setup. So here some basic captured like sorry, how many number of samples we can generate, what's like can we do is end-to-end training. So all these things we have discussed in the paper, what is in this work. So most of the things like for example, in this table we can actually see the impact of a particular loss. So the suppose we are not using the adversarial loss of the discriminator, then model is not converged. So here because generating the natural images, we need a GAN discriminator to learn the what we generate some images. But warrant we are making earlier source data is not available even through from the 10% is prepared the labeled source data. No, we are not using the source data, we are generating the source data. So GANs sorry yeah yeah, so here we are not using any source data, we only provided the labels. So this is the target data. So you can see, okay, I will show this source data. What is the source data? So this is the source data, MNIST is the source data, middle one, MNIST M is the target data, and this is generated data. So generated data, you can see this not similar to the source data. It's not, because it's not similar to the source data, it's actually similar to the target data, and we want our model to generate adapt it for the targets. It's very good for us because we are obtaining the data which are more look like to the target data. So we are not using this the MNIST data here anywhere in this learning method. We just use only the classifier which is trained on the MNIST data itself. So I hope I answer your questions. Maybe
The cross entropy loss that you're computing,
yes.
the label for that is coming from.
No. So suppose I give some random label digit 5 layer here, and it's some condition.
Okay.
So this is the ground truth label. I mean, this is a pseudo
Yeah,
ground truth label
got
for
it.
generated images.
Got it.
Based on this, we obtain the cross entropy loss.
Okay. Your condition was on the class. Sorry.
Yes.
I missed.
Yes.
Got it.
So we don't need any labels for here. We don't need any what we can say the source data. We just use unlabeled data. We are generating it from the GANs. So this is some mathematical question. I'm not going to discuss this thing because like it takes some more time. Based on I can tell about the motivation and the basic idea about this method. So this actually gives very good performance as compared to. So we also have done some lot of experiment how many samples are required if we do the end-to-end training, what will happen. So this is some results or analysis on this method. And this is a basic visualization of the generated samples. Like, so as I told that the generated samples more look like the target sample. Reason is that because the GANs the samples we are passing to the discriminator, the naturality of these samples is depend upon the real samples. So this samples, target samples, work as the real samples for the GANs. So GANs try to generate samples which so look like to this one, but they have some class information property using this pretrained classifier. Then we can have the label we can have the label and we can have the source information. One more thing, like how how we can divide these three examples in I mean, suppose this is target sample, this is a source sample, and this sample is the source or target. And what we can say, because this is not target, this is not source. That's why we use the energy what we can say the what means the energy of energy functions of to visualize these things. So I think I missed that slide. So where we can see that this actually generated samples lies between these two domains. Like suppose here is the source here the target, and in between the generated samples are here. So it's in between or more close to the target samples actually. This is not exactly target samples. This looks like the target samples, but and this is not this is some far from the source domain. Based on the energy visualization. I think I should have that thing, but yeah. Okay, so that's the basic summary of the methods. Like we use more. So this approach is more generic. I mean, this is not only limited to the domain adaptation. It can use any other where we don't have the actual data. We can generate data and use that data for any particular task. So this is the conclusion of this talk. Like we will discuss about some basic variant of the discriminator, for example, informative discriminator, probabilistic discriminator, to how to obtain the domain invariant features. And some last part we have discussed about the method where we don't need a source data for adaptation. Okay, so this is like a feature. So it can be like a very real time. So domain adaptation method is a very what we can say, very much applicable in any other fields, like because most of the practical settings we don't have the labels, and the training and test distribution is sufficiently, I mean, they have more discrepancy as compared to like when we are doing in the labs or some basic particular setup. Maybe it's time for a question or some doubts you have. Yeah,
Vinod, you mentioned dropout discriminator. That was not in your slides, right?
I missed that because
Okay.
I took it will take a lot of time, so I just removed that part. Yeah.
Oh, by the way, just this is a bit of a different question. Like, I have the copy of your thesis? Can it be shared, or is it?
Thesis share, I don't know, because like this IITK policy, so it's not allowed to share the thesis. I don't know, maybe you can download the thesis from IITK, then IITK will like, so it's not, I mean, I don't know.
Okay,
because
okay.
IITK people not allowed to share the thesis, I guess. I'm not sure about it, but
I'll confirm with one of,
but all the my thesis are come from papers. So all, I mean, the thesis doesn't have any new content. It's like all the papers content. So I can share papers link. That's the same thing.
Okay. Yeah.
All the chapters have some separate paper, and all the papers published, so you can use that paper. So there is no issue in that thing.
Okay. Yeah. Thank you.
Thanks, Vinod, for a nice talk, for your spending your valuable time, first of all. I have been seeing a lot of works that are happening in the on this uncertainty modeling
Yes,
in the
yes,
recent past, right? So
yes,
I see a great scope there.
yes,
Thanks for presenting your works, whatever you have done. Uh, the quick question from my side is, but I see that class imbalance is one of the biggest source of bias.
yes.
Suppose say I'm currently working with a multi-source kind of a data,
Okay, okay.
right? So and my each of the source domains are highly imbalanced in classes. So, can you throw some insights on how I can get rid of the bias that can come from a domain which has more number of images, and it can influence on the detection of the objects in the domain where the number of images are low, right? So, can you throw some light on how I can deal with this kind of a scenario?
Okay, maybe what I understood your question is, suppose you have 5 domains, and one domains have some thousands of images, but in the second domain is only tens of hundred of images, correct?
Correct,
So
correct.
so in that case, the bias will move toward the thousand of the images, like they have because they have number of images are so in that case, maybe I mean, we can use some kind of actively. So this thousands of images are not all the images are all important. They have only some
Okay.
of the images have the what you can say, the more important rather than the image. So we can select, for example, the active learning kind of setup, where we only actively choose some of the images which can based on these images we can we will got the same improvement, I mean same performance, not improvement.
Mhm.
So that's way we can choose, and that will be that. After that we can adapt that models for these, so we can have the like similar number of images. So for example, in the incremental learning setup, I mean, I have also worked on the incremental learning setup.
Mhm.
When in the new task, we have to for the new task we can capture some of the images only. Like, I mean, suppose in the current task we have the 1,000 images, but in the next task we can only take only 20 images. So we can
Mhm.
select the 20 images based on importance, how they are important. So importance could becomes like we should not select the images which are more simple, I mean very easy to learn, and we cannot also select the images which is more tough. So we have to kind of some between them, like the images which have actually the learnable quality. I mean, the model can they can drive the model in particular direction. That image should be selected. So in the similar way, in the domain adaptation, multi-source domain adaptation, in this imbalance kind of data set, we can use a similar idea, I guess. As of now, I can only think about this in this way.
Okay, so when you mean by selection criteria, so
Mhm.
is this some kind of a heuristic that we will choose in advance,
Uh,
saying,
no, not heuristic. There are a lot of methods are coming. For example, in the initial incremental learning setup, people generally use the harding algorithms and all these things to select
Mhm.
samples. But based on the uncertainty measure, also, I mean, I have seen some of the papers related to the uncertainty estimation to obtain the actively selecting the samples. So that's way also we
Mhm.
can use. So for example, if you the uncertainty of the data uncertainty here, so we should
Mhm.
select the images which have the less data uncertainty. I mean, data
Mhm.
uncertainty is very harm for the model, because the data uncertainty will generally negatively impact on the model's learning. So we can
Mhm.
choose the sample which have, I mean, we can sort out the images based on the electric uncertainty, data uncertainty. We can
Mhm.
select the lower one, all these things. And we can also select the model uncertainty, and we can sort out them. And based on these two, where the model uncertainty is less and the data uncertainty also less, then we can select these two images kind of. I mean, we can design some kind of algorithm to how to obtain the, because model uncertainty, okay, we cannot select the lower model uncertainty images, because if we select the lower model uncertainty, it means that we are selecting very easy samples, and easy samples is
Mhm.
not important, I mean, in
Mhm.
general. So we have to select a high model uncertainty samples, but low data uncertainty sample. In that way, we can figure out how many overlap of the images. Then we can select those images. Some idea. I mean, we can use the uncertainty measure.
Okay. Got it. So that means high model uncertainty and less data uncertainty is the kind of samples that we need to select on.
Yes. One of the criteria. Maybe we can choose. There is some what means out of distributions uncertainty also there. So a lot of things are there. So I'm not sure about how to do it, but this is basic way we can approach. You can approach. Yeah.
Okay. Thanks very much, Vinod. So that's one of the question that I had. The other one was your blog, whatever web page that you're showing, doesn't have the latest publication, right? So is it going to be published sometime, or you just mentioned the title, but the PDF wasn't there as such? Was
which work you are talking about? I mean,
the latest work in your blog. Actually, I wasn't able to see it. So
maybe I didn't check. Yeah, so I will just. So it's a AAAI paper or some which conference paper?
AAAI paper, I think. Yeah.
Oh, so yeah. So actually, the conference I just submitted the camera ready version. I just have to upload that paper here.
Okay.
So this paper is not related to domain adaptation. It's related to the what we can say the fair learning. So how the model should be fair about the it should fair. It means like when we have bias toward one particular attributes. I mean, for example, the gender bias, or suppose in the basic examples of the fair learning is like when we are providing a credit card. So generally credit card will provide only the male customers because they have the more income as compared to the female. That's the bias models are biased in because data set have bias. So how to remove that part? That's the method actually. So this is most related to the computer vision part. Yeah.
Okay. Because I was very curious to understand more about bias-free learning. So
okay.
Yeah, that is the reason I was just checking your publication.
Okay, that's bias is a different. It's not a domain bias, but yeah, it could be related to this thing. So I will share the paper maybe in the next 1 and 2 days. I will update the paper in that page. Yeah.
Okay, perfectly all right. Thanks so much, Vinod, for your time, and that's all from my side. Yeah.
Okay. So any other questions, or I can stop my sharing screen? Yeah. Okay. Okay, then thank you all for
Vinod, I have one question. In the Bayesian discriminator,
yes.
Do they can you just go to that slide? Bayesian discriminator.
Yeah, sure. I will share my screen. Yes. Slide is visible, Ravi?
Yeah, now it is.
Yeah.
So here you're not doing any classification, right? You're doing classification only with the source.
No. Here the classification is like a domain classification only, like binary discriminator. So here we are not using a multi-class discriminator here. I mean, so this is a binary discriminator, basic discriminator GRL paper they have. Like the paper I shown in the part where the green and green, blue, and red images are there. This is the basic baseline model for this work. Yeah, not other. Yeah.
Okay. Yeah.
So we just use the uncertainty in this work, and view how to attend view the attention using. I mean, this is the baseline paper for us in that work.
Okay. Will you be trying out discriminator with your IDDA discriminator there? Should improve, right? Theoretically.
No, actually it's not improving. The reason is that when we have the multi classes, so the uncertainty is not well, what we can say, the good enough as compared to that thing. And one thing we also done that analysis, but we couldn't put in the paper. So the inside or what the intuition is that when we use the multi-class discriminator in the attention part. So it's not very obvious to attend which, I mean, so there is a lot of what can say, the noise. I mean, so when we are the multi-class things, so binary class classification is very easy, but when you the multi-class classification is very tough. So in that case, the uncertainty measure is not good. So
so from a model
try to
certainty
highlight it.
perspective, it is difficult. You mean?
Yes, that's this, yeah.
So the
Uh,
essentially Bayesian discriminator is only telling which part of the image it got the cue from to say if it is source domain or the target domain, right?
yes, that's it.
Okay. Okay, so now meeting will end in 5 minutes. So if any other questions, like first of all, really thank you, Vinod. Thanks a lot. This is very hot topic, so it's really nice. You agreed to give us the talk.
Okay, then I can.
Yeah, maybe you can just go to your last page to just see your URL, GitHub URL page, so that anyone just
okay. Oh, sorry,
yeah.
I stopped my sharing. Yeah.
I'll put it in my message here. No issues.
Yeah. So, yeah. This is yeah.
Yeah.
Just one quick question before meeting ends. Can you tell the number of samples that you actually made use of in your source and target from
Yes.
source and target domains in the
Okay,
previous show?
so I use the standard data set. So maybe I can go the data set slides where I have discussed. So I didn't mention the number of samples I can tell. So for example, here Office 31 data set, the Office domains have some 2,800 samples, and the Amazon, Amazon, the first domain is Amazon. It has a 2,800 samples around. And this is the DSLR. It says some 400 samples, 400, 500 samples, and the webcam has a 700 samples each. And the number of classes are 31. In the home image lab has, I think, 600 samples for each class, I guess. No, six total number of samples are 600, and the per class is the 50 samples, I guess. I'm not sure. And the Office home is a large data set. It's like more than like around 700, 7,000, 8,000 samples are there. I'm not sure. Yeah, but this is, so that's a more popular data set is the Office 31 data set. And for the digit data set, like it's a classical MNIST data set is some 50,000 training and 10,000 test set. And MNIST is a similar way, like it's a 50,000 training and 10,000 what can see the test set. So these are number of samples in general. There is one data set which I not evaluated our models on, the which is like some which has some lakhs of 1 lakh samples of the source and target both. Yeah. So the data set is called what's called, yeah, some I don't remember that it right now, but yeah.
Got it.